So we heard ARM TechCon 2013. So who are you?
My name is Gary Atkinson. I'm the Director of Emergent Technologies, part of the segment marketing team at ARM.
So what does it mean to be the Director of Emergent Technologies?
Well, what I'm looking at are any technologies that could have a significant impact on ARM's royalties longer term. So technologies that could create pull-through for new processors, microcontrollers, digital devices, mostly focused on the embedded space. I ran the embedded segment marketing group for the last couple of years. So I'm looking at new things, whether that could be new radio technologies, it could be how do you program massively parallel processors, those types of things.
Does that mean it might be something that's not an ARM processor somehow? Or is it always related with ARM CPUs?
Well, generally it would have to have some impact on pulling through CPUs. So they might not use ARM today, and I would encourage them to use ARM. Or if it is using ARM and it is going to be disruptive, it would have to be globally scalable. I'm looking for things that need to shift hundreds of millions of devices, but also, often we'd like it to have some sort of socioeconomic impact, right? So there are some major challenges in the world today around how do we grow enough food for the additional 2 billion people by 2050? Where do we get all the clean water from? Energy efficiency, healthcare, transport. There are some really big challenges out there that technology isn't going to solve the problem, but applying technology, and particularly around things like the Internet of Things, could really help alleviate those challenges.
So does that mean you're doing far out crazy research, or is it, what is it?
No, not really. So we have an R&D group that do the far out stuff, and they work with universities, and so we have an engagement with the university around the 1 cubic millimeter sensor that you may have seen talked about in Mike Muller, our CTO, has talked about it before. It gets injected into the eye and is used to measure the pressure for glaucoma patients. But you could take that millimeter cube sensor, it has a battery, a solar panel, a microcontroller and a pressure sensor on that. But you could replace that MEM sensor with some other type of sensing technology. And of course these things are now like the size of a grain of sand, right? So you could distribute these into concrete, into buildings, or they could be embedded into clothing. You could do all sorts of things with those types of things. So my role is more about the application of these new technologies and how they would be used in the real world, as opposed to new transistor technologies or something very deep within the processor itself.
So when you talk about a grain of sand sized sensor, is that an ARM CPU in there?
Yeah.
Well, it's an ARM.
It's an ARM CPU, yeah.
It's a tiny ARM. It's smaller than Cortex M0. What is it?
No, it uses a Cortex M0. So Cortex M0 in its native form is less than 0.1 millimeters squared. So it barely exists as far as the human eye is concerned. So you apply that with the appropriate amount of peripherals for it to become a working microcontroller or a cut down microcontroller. That's doing a very basic function, right? It has highly optimized code just to run on that very tiny device. But in the example of glaucoma patients, it means that it's much easier for the doctor to measure the pressure after the first time, because they would just wave something like a mobile phone near the face and take the reading from the radio. Other examples of innovative use of those types of technologies are pills, medicine that has no battery in it itself, but it has an anode and cathode within the pill, and the acid inside your stomach creates the battery, enough power so it generates a small radio signal so that you can gather data from the medicine from outside the body. So taking those sorts of advances in technology and thinking differently and applying that technology means that we can start to do some really interesting things.
Are you saying people are going to eat ARM processors?
Well, I mean, in the ingestible market is pretty big. So lots of people are talking about wearables and the Pebble watch and the Fitbit and the Nike Fuel Band. But there are lots of people working on health and chronic disease management systems like insulin delivery systems and things like that actually get embedded into the body. So there are many examples of people putting ARM processors inside humans and animals.
But the ARM processor inside the pill that people swallow, does that work, or is it just a concept idea or something? Have people actually tried doing it?
That's actually been done, and it's in prototype stage right now, but it's being used to just deliver information about when that medicine was taken. One of the big challenges with some diseases and medicine in general is it has to be taken at a specific time, or just before or just after food, and humans are fallible, right? They forget to take it, they take it at the wrong time, and this is really just to be able to track accurately that you took that medicine at the right time in the right dose.
So to make sure it knows when you take it, you have to eat it.
Well, you have to eat it, yes. Yeah. So well, that's how you usually take pills. But rather than having a cap on the top of the bottle that tells you when it was taken off and taken back on again, there are many people who are forced to take, not forced, but they're resistant to taking medicine, and they will circumvent that system. They'll take the cap off and not take the medicine. The only way you know it's been taken is if you can get a signal from the medicine from inside the stomach.
Is that Cortex M0 in the pill?
I actually don't know what's in the pill. The prototype may or may not have an ARM processor in it at all. I don't know that for definite. But the mechanism of actually using the acid inside your stomach to be the battery power is quite innovative.
So the Cortex M0 is made on silicon, like all, is it silicon that it's called? All processors are made that on silicon
they're all,
material?
Well, right now they're all on silicon. There are some interesting advances in printable electronics where you, not so much print, there's two different types. One is a bit like inkjet printing, where you can print transistors onto a substrate, but they only have a maximum resolution, whereas the one that's gaining most traction now is imprintable electronics, where you the same mechanism you'd use to make a CD or a DVD by stamping the disc, you can use that to generate gates on a piece of flexible material, which becomes a computer of some description. Right now they can do a few thousand gates, so you could do a basic state machine type capability, but over time, you could get 12K gates for a Cortex M0 plus some storage and other peripherals. If you could get up to 200,000 gates, you've got a full microcontroller that's printable on roll-to-roll flexible material and just ship these things out in the hundreds of millions a day.
How soon is that going to work?
I would say we're probably within the next 5 years would be able to do that.
Quite sure it's going to work?
Yeah, I mean they've got working prototypes right now using fairly simple constructs, but over time, as they can shrink that and they can become more accurate and they improve the processing, well then you'll be able to get those microcontroller type capabilities down onto plastic.
So you were saying that the grain of salt sized Cortex M0 is 12,000 gates? Is that what it's called?
A basic Cortex M0 Plus is 12,000 gates, I believe. But then you have peripherals around the outside and flash memory and other pieces, so that's where a typical MCU will be, up to about 100 to 200,000 gates.
But I mean, the peripherals are not inside that grain of salt, right? That's somewhere else in the system, right? That's in the PCB, or what do you call it?
No, so the 1mm cube sensor I was talking about before, that has a full MCU capability built into it. So it's gathering sensor data, and it's drawing energy. So there's a tiny solar cell that's charging the little battery pack that's on there, and it is measuring the pressure inside the eye, and it's taking that data, and then when triggered by an active NFC reader, it transmits that data over NFC in order to pull that data out of the eye. So it's in the concept of a sensor, it is a fully functioning sensing system.
Everything is on that millimeter, smaller than millimeter square. Everything's there.
Everything is, that whole thing is less than 1 millimeter cubed, 1 by 1 by 1 millimeter cubed. Yeah.
Is that like saying it's a 1 millimeter cube PCB with the SoC? No, it's not. Nothing to do.
It's a 1 millimeter cube sensor. So it's the same as having a passive infrared sensor for a security system. It is a fully configured system injected into the eye, and it will deliver pressure readings to the doctor so that they can give you the appropriate amount of medicine.
So when people talk about 50 billion connected devices in 2020, that doesn't include all the hundreds of billions of sensors, or is that including all sensors?
It does today. So they consider all of these sensors that are being built, that is included in that number. But I think most of those numbers are pretty conservative. And actually, some people are talking about trillions of devices. If you can reliably manufacture a millimeter cube sensor to be put into concrete, for example. So the concrete industry loses 10 to 15% of the concrete in the world through theft. So the guys driving the truck, they're heading towards the building site, and they turn left and they sell their concrete for cash. They go back and fill up again, and they drive back to site. Right? There's no way of tracking where that concrete went and where it's being delivered. And if you think that's a raw material, right? So it's tens of billions of dollars a year in raw material. Once you scale that up to actually buildings, it's a huge amount of money lost out of that ecosystem. And if you could put very small sensing technology into that concrete, not only would you have a fingerprint of this is the particular batch and it's supposed to be in this building, but also it would be able to take thermal energy, because concrete is exothermic. It gets hot when it sets. So it generates heat. You could use that heat using energy harvesting to power the sensors inside the concrete, and you would get a really accurate picture of how that building is setting and how strong it is. And then for a period after that time, you could also get inbuilt stress measurements of that building as it's being used. Potentially, you could excite those sensors again in the future using some sort of energy delivery system to understand if it's still safe after an earthquake or some sort of accident. So if you start to look at those types of devices being deployed in the world, then 50 billion is nothing, right? These are going to be hundreds and hundreds and hundreds of billions of devices.
Hundreds of trillions?
Well, potentially. I mean,
but how quickly can it suddenly be real?
Well, so there are some real challenges in manufacturing. I mean, those 1 millimeter cube sensors that I talked about, that's a research program in a university. They're handmade. How you would make that in a volume manufacturing capability. How do you make it? Because they would need to be really cheap. Right? I mean, they would need to be tens of cents each, not tens of dollars each. So there's still a little bit of a way to go. 2020, we'll probably see some of these appearing in their different forms, particularly where you need very lightweight and not very long life, because they're not designed to be constantly running for 10 years. This is probably a 3-month, 6-month type capability.
Shouldn't we have like sensors in every chair, everywhere, on the floor, in the jacket, is that happening?
Well, we could see that happening. I mean, we're not that far away from that. These types of chairs in this hotel complex, having a tag on it so you know exactly where those chairs are at any one time, we're not far from being able to do that. Is it economically viable to do it today where those sensors are able to transmit their location and talk wirelessly to a gateway?
Which seats are available, stuff like that?
Well, you could do that, but there'd have to be a return on investment in order to do that, because that was still going to be reasonably costly when you're talking about thousands of chairs. So is there the value there to say there are 6 spare seats in here here's where they are, within an auditorium for a large Beyonce concert where tickets are $100 each? Then you could probably justify doing that, but with a conference centre chairs, the cost maybe isn't worth the effort.
And you would need to somehow power it by people sitting on the, or by the air, or where's the power coming from? You don't want to wire everything up, do you?
Well, no. You could put full systems on there with batteries that could last 5 to 10 years, depending on their duty cycle. But also you could use energy harvesting technologies are really coming along now, and you can harvest energy from the RF, so radio frequency around us. If you could put an appropriate antenna, maybe on the base of the chair, just the RF in the air could be enough to power up a supercapacitor, and then when you sit on the chair, that triggers this seat is full, and it could transmit its data.
Nice.
So gathering energy from RF, you could use thermal, so that your body heat could be a differential and generate electricity. You could use solar. Of course, inside a closed room like this, that isn't so useful. You could use kinetic energy, like you say. The action of sitting on the chair could generate enough power for it to transmit its data. So those are too expensive today to be put on every seat. But as those technologies improve and the manufacturing costs come down, you already get light switches that have no batteries in them, and when you press the switch, that is enough energy to generate the signal to turn the light on.
Does that mean just the Wi-Fi pollution kind of that's in the air is enough to power everything? Or is it not only Wi-Fi? Which RF would it be?
Well,
new RF or existing RF?
No, you just harness existing RF. So you would tune the antenna for that particular RF, but things like digital television signals, they're relatively powerful. We don't see them. They're sub 1 gigahertz, somewhere between 470 and 790 megahertz. And there is enough energy there to power a good number of sensors within a room like this. And it's spare energy, right? It's just flowing through this room every minute of every day, and if you could harness some of that, you could make good use of that.
So you talk about the TV spectrum.
Yes.
So what are you working on with the white space?
Well, so apart from powering small sensors using energy harvesting, one of the other big areas that is interesting for TV spectrum is that there is a lot of spare capacity in that. So you can't re-farm that spectrum because it's already been allocated to the television broadcasters, it's been allocated to places like this that use digital microphones, but there's still plenty of capacity there. And so ARM is involved in a special interest groups trying to set a new machine-to-machine standard for wireless communications over long range called Weightless. So it's the Weightless SIG, the website's weightless.org, and ARM in conjunction with Newell and Cable and Wireless and CSR and also now Accenture as promoter members, we would like to see this new radio technology be used to communicate particularly over long distances. Inside a building like this, you've got 802.15.4 radios like Zigbee and Z-Wave and Bluetooth LE, relatively short distances, low power, very low cost. They're all good solutions. But when you leave a building, we have what I call the connectivity gap. You're now into cellular and satellite, and those are often too expensive, they consume too much power. You get the range, but you don't get that cost model that you get with Bluetooth LE. And Weightless aims to bridge that connectivity gap. So you will have a sub $2 chip that will last for 10 years on a coin cell battery, but can have a range of up to 10 kilometers, so 5 to 6 miles. So now you can put down a base station, cover 10 to 16 square miles of area. You can talk to 100,000 devices on one base station. So now you can put humidity sensors in farmland to accurately control irrigation systems. So you only water the piece of the field that needs it, not the entire field. You can use it to monitor the quality of water in rivers. You could use it for a forest fire detection grid to warn people that there is a forest fire, because often we don't know about it until it's too late. So you can do some of this with long-range mesh technologies, but in order to, if I'm based over here and I want to measure something over there, I need to create a multi-hop mesh in order to get to that point. Whereas with Weightless, you could drop down a base station, and as long as you're within 5 miles of that base station, you could put your sensor wherever you like. So you could put out 10, and then put out 50, and then put out 1,000, and then put out 20,000. You don't have to do everything in one go in order to get that coverage. So I see Weightless is going to be very disruptive from how do we gather more data, use that data to make better decisions, and then become more efficient about how we grow food, how we produce clean water, how we become more energy efficient, and how do we address this growing healthcare problem.
So when you say 100,000 from one base station, a pocket hotspot on Wi-Fi has a limit of 5. How is it possible to have 100,000 from one base station?
So we're using, so most of the time you will transmit in a predefined time space, right? The thing about machine to machine is they don't usually think, oh, I need to phone my mum, it's her birthday, right? I mean, there is not this, we have to scale the platform in order to be available for humans to make calls or do video chat or whatever we need to do, which is how our current cellular systems are built. In the machine world, if it sends the data now or in 5 seconds or in 1 minute's time, it doesn't really matter, and they are very short packets of data. So simultaneously on one base station, you won't have 100,000. It will support 100,000 devices, but they'll wake up every 15 minutes, see if I need to do anything or not. But some of them will just be deployed, say, as a vibration sensor on a water treatment plant in the middle of nowhere. It's monitoring the vibration. The microcontroller inside is running an algorithm to check that the waveform is consistent. But if that starts to deviate, then it sends a message to say a bearing's gone on the motor, or something's going wrong. So at least they don't have to send a guy out every 6 months to check on it. They only go to fix it when it needs fixing. But that might not send data, for years. So the thing about Weightless is that you only pay for the data that you send. So you can put sensors in places that you could never afford to do it today, because you'd have to take out a cellular contract or a satellite contract, and you'll be paying monthly just for that one packet of data you need to send that says, I've gone wrong. So Weightless is designed to be highly scalable. It's designed for very small packets of data. There are no latency guarantees. It's not about, there's an emergency, I need to send lots of data. It will support that, but most of the time it is, am I hot, am I cold, is it light, is it dark, what's the pressure, what's my vibration profile look like. So it's about sending small packets of data so we can make better decisions.
So how is it going to work to have this system where people, are they going to pay for data? How? And is that cost inside when they buy the device or later, or is it some kind of subscription?
Well, it's a good question. So normally it would be subscription based. You probably wouldn't have one device. So these are about private network operators. It could be an oil company on a refinery or oil rigs. It could be a forestry commission that just want to protect the forest and monitor the forest. So they will have tens of thousands of devices. I think we will see those devices either being on an all-you-can-eat plan, depending on the sorts of volumes. But if you just had a handful of devices, you're probably looking at a couple of dollars a year per device from an operational cost. So the costs themselves for the device will be down in the order of $10 to $20 for the sensor, probably getting down to $5 over time. And then you have to budget for a couple of dollars a year per device to get that data back to where it needs to be. It means you have a cost point that is much more scalable than you can do today using traditional cellular technologies.
So basically you have an account and all the devices that you buy are tied with your account somehow, and that's easy to do?
Yes, yeah. I mean, that comes down to the network management and the services that are delivered. Our focus with Weightless is getting that physical infrastructure deployed, and then the network as a service piece that allows any operator to run that as part of their network. And then you would integrate that into either an existing OSS and BSS system from an operator perspective, or if you're the owner-operator of your own network, like the forests or the coastal monitoring groups or whatever they are, they would just run that as an operational cost. And they would just use their own internet backhaul to get the data into the cloud and do whatever they need to do. So from a public network perspective, yes, you would have a handful of devices or a few hundred devices, and you would have an account and pay a monthly subscription.
So how much does it cost to make your own hotspot on this system? Is it possible to make a $10 Weightless hotspot, like a Wi-Fi hotspot?
No. So, this is designed as this is a large-scale cellular deployment, right? It's an order of magnitude cheaper than doing 3G or LTE, but it's not for the consumer to build in their own home, right?
Is it possible? Well, wouldn't there be like some smaller hotspots on that same spectrum somehow?
The real benefit of it is that it has this large scale. So in your local community, wherever you have a telephone exchange or a cable head end, you could have a Weightless base station there and it would cover the entire community, right? So up until 100, 150,000 devices, if it really starts to get heavily used, then you would put another base station up and run that on a different channel and then have the devices talk to that. Could you have a consumer variant in the future? Well, maybe, but you're not really in that, to create your own hotspot inside of your home, you may as well use a Zigbee gateway. You're achieving the same benefit, really.
So what I was imagining, but maybe it's just wrong, is when people were talking about white spaces, I was thinking about, like the phone hotspot sharing, where everybody would have like a new router they would install at home on the ADSL, and
right.
they would cover maybe 500 meters or something around their home, and everybody would do that, and then suddenly there's free wireless broadband for everybody.
So it's not broadband, right? So when I say we can do 100,000 devices over 4 or 5 miles, we're talking about 100 kilobit per second link, right? So this is relatively slow data rates from our perspective. You're probably going to be sending somewhere less than 100 bytes per message. So it really is about what's the temperature, what's the humidity, what's the pressure, those types of information. Now, if you have a large property or a small farm or an estate or something like that, would you put up your own base station for the amount of sensors that you could have in and around that? Then yes, maybe. But for the average home user, it would be much more cost effective to just link onto whatever the white space base station is in their community.
But can't you use white space with fast data rates also?
You can. So the technology that Newell have developed as the first implementer of white space, they did have some software development kits that could use the full bandwidth of one channel, which means you could get about 16 megabits per second. So there are some people researching the use of white space in places like Africa in order to be able to deliver backhaul technology for Wi-Fi hotspots, for example. So it can be done. 16 megabits per second. But for me, the really interesting use of white space is using weightless and having hundreds of thousands of devices, because of course the spectrum costs nothing. So it means the capital cost of infrastructure is very low, the barrier to entry is very low, and the operational cost of those devices is very low.
But can you have both? And like in cities, have both? Like
have
some kind of like alternative to 3G or 4G, and also do all the devices?
Well, in cities there's a challenge because usually you don't have very many white space channels available, right? So, New York, San Jose, where we are now, San Francisco, there are very few white space channels available because there are lots of TV channels. So the spectrum is saturated in some metropolitan areas. For alternatives to 3G broadband, having Wi-Fi in the streets provided by a service provider is probably the better way to go.
But can you just lower the power and have more base stations and then make it work?
Well, the regulations as defined by the FCC, if a channel is already allocated to a television channel, it doesn't matter how much you turn the power down, you're not allowed to use it.
All right. Yeah. Okay, so what are you going to do here at the ArmTechCon?
So here I'm having a number of meetings with people that are doing some interesting new things. I'm exploring what some of our partners are doing with relation to any new products that they're bringing out. I will continue to talk about weightless and where we are with that development and when it's going to become a Also just absorbing some of the conversations and the community feel that goes on around the ARM ecosystem. And seeing what some people are doing that I don't know about. And can I put that together with something else to help solve a particular problem? That's the sort of things that I'm interested in.
And how soon is weightless happening?
So weightless has silicon today. So there is a chip from Newell called Iceni. They are working on modules. There are second generation of base stations. They're doing pilot deployments in the UK and in the US. But I think we'll see real deployments, commercial deployments, in the second half of 2014.